Let's kick things off. I'm so delighted to be able to welcome all of you to Angie Boggust's PhD defense. The PhD defense is always such a special moment, and I'm so glad to see, we've been able to fill out the room. There are like 20 or 30 people on Zoom. Special shout out to Angie's family who's been able to join us in person, which I think is always really fun. And as we're about to see, Angie is just a truly exceptional researcher. That's something that has been clear to me from the very day that I met her. It was my first year here at MIT. And luckily for me, I developed this new class on interactive visualization. And one of the first emails I got was from a student named Angie saying, is this class actually available? Because I'm really interested in taking it. And she was such a star student, even in the context of just the class, to the degree that even today, 6 or 7 years later, we continue to use Angie's work as sort of the exemplary kinds of things that we're expecting from students in the class. But it's really the sort of the final project that she chose to work on that was kind of the standout. So, cast your minds back 6 or 7 years ago, right? This is way before ChatGPT, but machine learning was already a pretty big thing. And there was this nascent, incipient area of interpretability. But this area was sort of dominated by these extremely complex, barely usable dashboards to make sense of these machine learning models. And almost all of them were geared towards other expert machine learning developers, right? But Angie's project was, to my knowledge, at least one of the first that thought really hard about what it means to make interpretability usable and useful for people that aren't experts in machine learning, but want to use some of these models in their own work. And it was such a standout that, we host an exhibition of these projects every year. And, like multiple visitors came up to me after calling out Angie's work to say, when can I use this? Like, this is so cool. And, she got an internship off of that. It turned into a nice long collaboration over the years. And I think it's the sort of project that demonstrates Angie's incredible ability to sort of skate where the puck is going, right? We see this even in her second project. Yeah, that was a hockey.
Yeah,
good.
Thank
you. Yeah.
Know your audience.
Yeah, exactly. It was something that was true even in her second project, right? So this is in the depths of the pandemic, 2020. And, as a research community, we were kind of arguing amongst ourselves, what even is interpretability? How do we define it? But Angie locked in on the fact that it was all about alignment, right? Aligning users' mental models to the outputs of these machine learning models. The problem, though, is that when you are a couple of steps ahead of the rest of the research community kind of doesn't get what you're working on, right? And so the start of Angie's PhD was sort of characterized, unfortunately, by a string of repeated rejections. And this was something that I was able to really empathize with because that was also how my PhD started. I went through, I think, 5 or 6 paper rejections to the degree that at one point in my PhD, by my second or third year, I was like, maybe I should drop out, right? Like, maybe this is not for me. But I never heard that from Angie. Like, every rejection she faced, it was just like, all right, we'll just double down. We'll make this paper better, right? It was just like dust off her shoulder, completely unfazed. And she had the last laugh because both those papers ended up winning awards at the premier conferences in human-computer interaction and human AI interaction. And since then, she's gone on to win even more awards, including the Apple PhD Fellowship. Now, I could spend a lot more time sort of like enumerating all the things that we clearly know are fabulous about Angie, but, I would rather hear from her. Suffice to say that, in the visualization group here at MIT, we're going to miss her dearly when she graduates. And so before I turn things over to her, one last point on logistics. So once Angie is done presenting her work, we'll take questions from all of you, the audience, as well as folks on Zoom. And then after that, we will move into a closed session with Angie's PhD committee. Assuming everything goes well, we will celebrate the almost Dr. Angie Boggust at the HCI Lounge on the 7th floor. There's a lot of folks who can help walk folks over there. So without further ado, please join me in welcoming Angie.
Wow, okay. Thank you so much for that introduction. I feel like I can skip my whole intro because you did it. But yes, I'm Angie. Thank you all so much for coming. I'm really excited to chat about the research I've been doing on designing beneficial human-AI interactions by reconciling between AI representations and people's mental models. So I'm going to start by stating the obvious and say that AI has really proliferated into so many areas of our lives. And it's now become our collaborator, right? It acts as our assistant, it helps us debug our code, and it monitors our health. And as we design these systems, we're ultimately working towards this goal of human-AI alignment, a future where AI systems abide by the goals and the values of their human users and society. And as it stands, alignment has been incredibly useful in helping us make models that work well and work safely. So typically we start with a model that's gone through pre-training, and so as a result, it's formed a representation of the world, but that representation isn't necessarily human-like. And so to do that, and as a result of it not being human-like, it can often be unhelpful and also unsafe. So before sort of post-training and alignment, your favorite large language model chatbot actually isn't a chatbot at all. It's a next phrase continuer. So if I ask what's the capital of Canada, instead of answering me, it's going to try to finish that phrase and turn it into a multiple choice question. And it can also be unsafe and violate really basic human values like respect and lawfulness and respond to harmful requests like to write a phishing email. And so alignment training has been how we fix these issues, right? We collect a bunch of human preferences, and then we train our model on them in hopes that we get a more human-like representation of the world. We now get a model that's able to answer questions the way that we do, and it's able to uphold our values and refuse harmful requests. And so this process of model alignment has really been what spurred many of the AI capabilities that we've come to appreciate today. But when we use AI systems, people care more than just about alignment to goals and values. And so to give you an example, here's a chat that I had recently with Google Gemini, where I'm asking it to critique my paper abstract. And by all accounts, the model is quite aligned to my goals and values, right? It's answering the question that I asked it, it's doing the task I requested, and it's also doing so in a very respectful way. But when I think about what alignment means in this context, I have a mental model of how I write an abstract and the type of feedback that I might want on that. And it's really unclear whether Gemini aligns with that, right? So for instance, there's all these contextual aspects of alignment, like knowledge. Is this feedback that I'm going to get from someone like my advisor? Is this feedback that I'm going to get from a layperson? Does it share my reasoning, right? I said this is going to a particular conference. Is it reasoning over the sort of norms of that conference and reflecting that? And what concepts is it reflecting? Does it understand the field the way I do? Do we consider the same ideas to be seminal? These aren't things that we typically consider to be part of alignment, but they're really important for me to understand in order to decide how I'm going to interact with this model moving forward. And so if these things are important, why don't we have them? And there's a few differences that exist between how we think about alignment to goals and values and how we think about alignment in context. First and foremost, when we think about goals and values, they're nearly almost collectively agreed upon, right? So when I say that I want a model to be respectful, I think most of us would agree that that's a good thing. And as a result, it means that misalignment is bad. If a model is misaligned with our values, it can be harmful, it can be malicious. And as a result of these two properties, it means it's encodable during development, right? We can collect a bunch of human data and we can generalize these things from it, encode it in the model, and then deploy it nearly unilaterally across users. Whereas when we think about what it means to be aligned to things like knowledge and reasoning, it's going to depend on who is using the model, the domain they're using it in, the task they're using it for. The way that I expect a model to give me feedback on a machine learning paper is going to be different than how a biologist might get feedback for a science journal. And as a result, misalignment isn't necessarily always a problem, right? The way that we might go to a collaborator that has diverse expertise or diverse knowledge to complement our own, that's something that I want. And so it's not always bad to be misaligned here. And as a result, this is something that we have to negotiate in domain with the person using the model on the task that they're using it for. And so instead of thinking about how to make AI models and their users more and more aligned, where we want the user's mental model to match its AI's representations, I've instead been thinking about how we could support these more contextualized aspects of alignment through reconciliation. to allow people to have the agency to understand and control their model's representations without those representations needing to be identical to their own. And so reconciling between mental models is actually something that we do all of the time as people when we interact with others, right? So for instance, in healthcare, we convene tumor boards of medical specialists who have different mental models of disease presentation and work together to ultimately decide on optimal patient care. And in science, as many of us know, interdisciplinary collaborations are often what helps us solve really challenging problems, right? Where, for instance, biologists and chemists might reconcile their understanding of molecular interactions to ultimately aid in drug discovery. And so my research aims to ensure equally beneficial human-AI collaborations by helping people do the same process of reconciliation, but instead of with another person, with their AI model. And so today I want to talk about some ways we can do this. First, we're going to look at how we can communicate model concepts in a way that helps people understand model behavior. And then we're going to kind of pop up a level and we're going to compare higher level aspects of cognition. And we're going to compare model reasoning as well as model knowledge. And through this, we're going to find that by giving people the ability to understand their model's representations, they're going to be able to improve their AI interactions, they're going to be able to improve their model's alignment, and they're even going to be able to improve human knowledge. So in order to reconcile with an AI model, users need to understand how their model represents the world. But the problem is that models' representations are in high-dimensional space. It means that they encode their concepts as latent vectors. And just looking at these vectors, it's not clear exactly which concept that corresponds with. And so we need to be able to translate these vectors into something that people are able to understand, and that is ultimately faithful to what the model has represented. So to translate these vectors into concepts, we often start by looking at the data that activates it. So here we see that for this concept, we're activating on the idea of covering the news, right? So journalists who covered the story, journalists covering famine, his channel was covering the issue. And then we can take these patterns and we can feed them through a large language model and get back a description of what this concept is. Here we get back verbs related to journalism that denote the act of covering or reporting events, often in a critical context. Now, these descriptions are super helpful, but they're often convoluted, even for pretty simple concepts like this one, right? We get back a pretty dense description of what this concept is. And they also contain ambiguity. So here we see that it includes this clause often in a critical context. But what is a critical context? Is all news critical? And so it's really unclear exactly what concept my model has learned here. And so even though we've translated this into an understandable format, it's not clear what this concept is. And in the past, when we've run into similar issues with natural language, we've turned to structured languages. We designed programming languages to describe computation. We designed regular languages and regular expressions to do pattern matching. And so our question was, could we define a structured language that similarly gave us more precision to describe what these concepts are? Could we design a structured language that matches the patterns of model concepts using a syntax that gives us structure while also allowing for some conceptual flexibility? And here, could we say that our concept corresponds to variations of the word cover in the context of journalism? So to answer this question, we created Semantic Regexes, which are a structured language description of model concepts. And our language consists of primitives that match common patterns for model concepts, like matching an exact phrase or syntactic or semantic variants of that phrase. And then we combine this with modifiers that expand or refine its scope. So for instance, only matching in a particular context, or having multiple phrases in sequence or in alternation. And in doing so, what I like about this is we're able to combine the structure that you get from syntax with the flexibility you get from natural language. So you can kind of slot in any word or phrase into any one of these syntax tags, and you add flexibility that way. And what we find is that semantic regexes help people understand their model's concepts. So despite using a constrained syntax, we can describe just as many concepts as natural language can, while being more concise and consistent. So for instance, this concept activates on variations of the word run. And we can describe this simply as the lexeme run. And here we're borrowing from linguistics, but a lexeme is a syntactic variant of a word. So people better understand concepts when given a semantic regex. And we see this here. Each row in this table is a concept, and the ones highlighted in red, people did a better job of understanding what the concept was when given a semantic regex as compared to natural language. And one reason for this is that we spell it out via pattern, right? So this concept here activates on times in the evening. So anything that's like a time and then PM. And in our semantic regex, we just spell that out, right? It's variations of times followed by exactly the symbol PM. And as a result, when people saw this, they were able to generate, they knew what would activate this concept, right? They were able to generate a bunch of text that fit in this concept, and they understood what the boundaries of that were. Whereas with natural language, it's more ambiguous, right? And we're indicating hours in the PM format. And so some people thought any sort of hour in the evening was what our model has learned. And it also allows people to study new aspects of conceptual alignment. So for instance, unlike natural language, we have syntax, and we can actually encode the complexity of a concept via the syntax. So simple concepts we can represent as often singular low-level primitives, like the lexeme run, which we saw before. Whereas more complex concepts can require multiple primitives used with modifiers and sort of combinations of them. And as a result, we can kind of just read this straight off and see here that conceptual complexity increases as we move deeper in the model. So sort of similar to the idea that in human thinking, we might start with a really simple concept and then build that up into a more complex idea. And so with semantic regexes, we've simply just designed a better way to communicate model concepts to people. And this is important because it allows them to both identify and study how their model represents concepts that are important to their domain and their task, right? Like its understanding of particular drugs or its conceptualization of programming. And since the syntax of semantic regex encodes and affords complexity, people can do new types of model representational analysis, like studying complexity across the model. And so with semantic regexes, people are able to reconcile between how a model represents concepts in their domain. And this gives us really fine-grained detail, right, into individual concepts. But we often want to know whether our model aligns with higher-level cognitive processes. So for instance, does it align with our reasoning? Does it follow our domain knowledge? And so we're going to look at ways that we can do this as well. Now, reconciling these higher level aspects of cognition is actually something we do all the time in human collaborations. So for instance, we often will explain our reasoning process by simply explaining our decision, right? For instance, doctors might discuss the attributes that led them to a particular diagnosis, like the shape or the color of the skin lesion. And in doing so, it helps us sort of understand where our collaborator is coming from, and build trust in their decision-making process as a whole. Now, when we collaborate with AI models, we can obviously still get users' explanations. And thanks to interpretability, we can also get model explanations for their decisions. But while user explanations are often in the form of sort of high-level semantic concepts like color and shape, a common way that we get model explanations is via feature attribution. And so here what you're looking at is essentially the importance of every pixel in this image to the model. And so here, the brighter the spots, the more important it was. So the sort of the circle on the right-hand side of the image was the most important to the model. But this mismatch in format can be a problem because what actually ends up happening in practice is that people have to individually look at each of these explanations and then compare to what they're seeing in the image, right? They have to sort of highlight that there's a circle on the right-hand side and then map that to features that they might be seeing when they look at that image. And as a result, it can be sort of tedious to do for many examples. And it can be hard for people to fully ensure that they understand their model's reasoning process across sort of the suite of decisions that this model is going to have to make, right? If we deploy this model in a real diagnostic scenario, it's going to see many, many, many lesions, and I want to make sure that its reasoning process is aligned with mine across all of those, not just the few that I was able to mentally look at. And so to make explanation sharing more systematic and scalable, we introduced a set of metrics and interactions that are called shared interest. And it does so by turning human explanations via annotations over the image, and then we discretize model explanations, and as a result, we now have explanations in the same representation space. They're now represented as sets of image pixels. And as a result, this makes them directly and set theoretically comparable. So we can now sort of quantify and measure the difference in explanation here. And we introduced 3 metrics to help us do that quantification process. And they each describe the extent to which the model and user's explanation agrees or diverges from each other. Now, under a low score, all of these metrics are going to indicate that the model and its user relied on a disjoint set of features. So for instance, in the top example, we can see the human has annotated the snowmobile, whereas the model is looking at the snowmobile helmet. Right, so we're reasoning over different sets of features. Whereas with a high score, we can start to see how these metrics are complementary to one another. So for instance, intersection over union is our strictest metric. It means that the model and the user are relying on the same set of features, right? They're both relying on our pixels of the dog. Saliency coverage is more akin to precision. So it means that the model relied on a subset of features that the user thought was important, like relying on just the dog's face as opposed to the entire dog. And then sort of conversely, ground truth coverage is more akin to recall. So it indicates that the model is relying on a superset of the user's important features, like using not just the race car, but also the surrounding context of the track. But what I like about these metrics is that instead of just reporting how, like if the model is aligned and sort of considering alignment to be this unidimensional axis from misaligned to aligned, we can instead split out and measure different aspects of how a model and user might be reasoning differently. It's a different form of misalignment to use a subset of my features than to use additional features beyond mine. And as a result, when we applied them across image and text domains and various data sets, we found 8 recurring patterns of model alignment that sort of describe how model and user reasoning intersects or diverges. And this pattern vocabulary allowed people to sort of shift their process from doing that individual inspection of particular images to be able to pop up a level and ask questions that were important to them. So for instance, users often want to know when a model complements their reasoning, and we can just translate this into a function of the shared interest metrics. So here we're going to filter to cases where the model makes the same decision as its user, but does so for a disjoint reason. And so here we see we would get back all the images, but as an example, we would get back this image where the model is relying on the snowmobile helmet as opposed to the snowmobile. Or alternatively, a model might ask, when does the model use features that I consider important to make a different decision? And so here we can translate this into insufficient subset cases where the model's explanation is using the user's feature, but results in a different outcome. And so when we use these patterns with real people, it improved their understanding of their models. So for instance, we worked with a dermatologist that used shared interest to audit a melanoma prediction model. And they used this pattern vocabulary to understand whether the model's reasoning process reflected their medical expectations. And so at one point, they filtered to cases where the model made a correct diagnosis, but for a different reasoning, like we just saw in our pattern vocabulary. And what they found was that there was a whole swath of cases where the model was relying on these image artifacts. So these blue, purple, and green sort of semicircles that you see off to the side of the images. And so in the best case scenario, this risks wasting a dermatologist's time because our model is making decisions based on non-medically valid features, and at worst could lead to potentially misdiagnoses or clinical problems. But by sort of framing this in terms of the dermatologist's thought process, they're able to, first and foremost, see that this was a sort of recurring issue across many, many examples. And they're also able to hypothesize how they might address this problem. So for instance, they considered, not including artifacts and any images that they were going to feed the model in the future, in manually analyzing ones that had to contain artifacts, or alternatively use this as a way to communicate with their model vendor what their expectations were for how a model should behave. So as a non-AI expert, it can be hard for them to communicate exactly what is and is not acceptable, but here they had a vocabulary that helped them be a more involved part of the model development process in their domain. And with shared interest, users were actually able to flip the script and sort of instead of asking if the model's explanation agreed with their reasoning process, they could ask if their reasoning process matched the model. So for instance, by annotating this person's hat, shared interest will return the model decisions whose rationales overlapped the most. And so here we see we get back types of hats like sombreros and cowboy hats. Whereas if we annotate this person's hand, we see that the return concepts are items that are likely to occur with a hand, like a notebook or a cleaver, which might suggest how we could inspect our data set for potentially spurious correlations or bias. And it also allows people to ask questions like how robust a model's understanding of a concept is. So if we annotate the entire dog, we get back dog breeds. If we annotate just the dog's face, we still get back types of dogs. And even if we just annotate the dog, a small area of the dog's snout, we see that we still get back types of dogs, sort of suggesting that our model has built up a comprehensive understanding of the characteristics that would make up a dog. And so in this way, users are able to test that the model is representing their task and that it aligns with their mental model. And so what I find exciting about shared interest is that just by communicating to them how the model reasoned, it actually empowered them to improve their AI interactions, right? By giving people the ability to ask and answer alignment questions that were important to them, they're able to mitigate misalignments by trading off decision-making or by speaking with their model vendor. And actually, since then, we and others have extended shared interest from sort of this qualitative auditing tool that I've showed you today to also be a quantitative benchmark. And we found that it's able to uncover bias that's not apparent from traditional evaluation metrics, as well as evaluate models in pretty high stakes domains like healthcare and also autonomous driving. And so in shared interest, we took inspiration from how collaborators share their mental models via explanation. But often, I'm going to argue that we don't actually need our collaborators to explain themselves in order to feel like we can trust them. Right? Often we can do that just from knowing them or even just knowing their background. Right? For instance, if I have two doctors, I expect that they have some sort of baseline form of medical domain knowledge. And as a result, when they're considering a skin disease, they're going to know that it could be a skin cancer like basal cell carcinoma or melanoma, or that it could be a skin inflammation disease like psoriasis. And as a result, I know that they understand each particular diagnosis and what their symptoms are, but I also know that they're going to understand the relationships between diseases that can be important, right? That can indicate what a treatment might be. And this helps me build trust that we have some sort of baseline understanding of the task that we're in. But despite being trained on immense amounts of data, we don't have this same understanding of our AI model's knowledge, right? Just because it can diagnose cancer accurately doesn't mean that it's necessarily doing so based on fundamental medical knowledge. And this is an issue for a lot of folks, including linguists and scientists, but doctors have a particularly endearing way of expressing this. They say they just want a model that's gone to medical school. And when they say that, what they mean is they just want to feel like the model has the same sort of shared domain knowledge that they'd expect from any physician colleague that they interact with, that they're starting from some sort of baseline level of domain understanding. But that's not typically something we evaluate models for, right? We test that they can do the task across a bunch of very challenging examples, but we don't necessarily test that they're reflective of underlying domain knowledge, right? We don't test if our models actually went to medical school. So to be able to test for this, we developed a method called abstraction alignment, and the intuition is really simple. It's that if a model represents the domain the same way as its user, then it should confuse semantically related concepts. So if our model understands skin diseases the same way as a physician, it should be more likely, on the whole, to confuse melanoma with other skin cancers like carcinoma, as opposed to a more unrelated disease like psoriasis. And so to measure this in practice, we start with the model's confidence across a bunch of concepts. And so, for instance, on this example, we can see that our model is 61% confidence in oak, 21% in willow, and 18% in maple. And that's not actually a very decisive distribution here, but I bet that you thought it was pretty acceptable. And that's because you just mentally measured abstraction alignment. You looked at all three of those concepts, you identified that they were types of trees, And he thought, oh, my model is just confusing different types of trees. And that's exactly what abstraction alignment does, except instead of comparing to your internalized understanding of the world, we're going to compare against an externalized knowledge graph. And so what we do is we link these concepts into a knowledge graph. For instance, this one reflects the biological categorizations of plants and animals. And so now we can see that we've grouped oak, willow, and maple as types of trees. And then we can actually sum their confidence up our knowledge graph and now be able to see quantitatively that our model is fully confident that this image is some sort of tree. We can do this for other examples. So for this image of an elephant, we see that our confidence is split across 3 distinct classes, including bears and mushrooms. And if we actually just look at the uncertainty of these 2 decisions on the output, our model is almost equally confused, right? We follow this approximately 60-20-20 distribution. It's only when we propagate that confidence up the knowledge graph that we can see the difference between these 2 decisions, right? I'm likely more okay with the confusion in the top example, even though my model is technically wrong here, because it's more aligned with my knowledge, right? It's just confusing types of trees. Whereas in the bottom example, I'm likely a little bit more concerned because even though the model is correct, I would be unlikely to confuse these concepts, right? I wouldn't typically confuse carnivores and vegetables. Not only does abstraction alignment help us see this, but we can also quantify this. We call these weighted abstraction graphs, and they're a somewhat dense data representation. So we have a set of metrics that helps us measure different things, including whether a model matches a user's semantics, whether it matches user's expected level of specificity, and whether it matches a user's generalization process, which is actually what we all just did via this visualization. We can do the same thing and turn it into a quantified metric. And so here we're just going to compare the difference in uncertainty or entropy when we move up the knowledge graph, right? So we just saw that they have the same output uncertainty at the lowest level. We're measuring this via entropy, but just think uncertainty. And then we're going to move one level up the knowledge graph and measure that uncertainty again. And now we have no uncertainty in the top example because we're fully confident it's a tree. But we still have the exact same amount of uncertainty in the bottom example because we're split across classes. And then we can compare how much uncertainty we reduced by generalizing. And now we have a quantifiable way to say that the top example is more aligned with my knowledge than the bottom example. And so with these metrics, we can both measure and improve how AI models adhere to user knowledge. In particular, we use them to study how language models generalize. And in this study, what we're doing is we're testing a language model's ability to answer factual questions. Here, we're going to be looking at a language model's ability to answer questions about someone's profession. And then we're going to compare this to a lexical graph that's going to map similar professions together, right? So painter and musician are going to be types of artists, geologists and biologists are going to be types of scientists. And in this particular example, we're looking at the model's ability to tell us what push-button objects profession is. Now, I wouldn't have known enough to be able to tell you that push-button objects is a composer, which is our label, but I probably would have known enough to be able to tell you that he's some sort of artist. And as people, we often prefer an answer to a question that's more general but correct over me making a very specific but likely incorrect guess. But we find that models actually often do the opposite. They often prefer a specific answer at the expense of correctness. And that's a problem because it can lead to sort of misleading answers from our model. But despite outputting the specific incorrect answer, if we actually compare against this knowledge graph and propagate our confidences up, we can see all this green confidence on the left. Our model is actually cumulatively much more confident that push-button objects is some sort of artist or some sort of creator. And I think this is exciting because it shows us 2 things. First, we might be measuring factual accuracy wrong. Here, we're going to rightly penalize the model for outputting photographer. But photographer is actually a much closer in semantic space. It's a much better guess than if I had told you that push-button objects was a civil engineer. And in evaluations, we don't typically distinguish how wrong an answer is. So when we use abstraction alignment in benchmarks, we find that models with the highest factual accuracy are not necessarily the models with the highest abstraction alignment or alignment to domain knowledge. Right here where we see actually our best factually accurate model is actually our worst, has the worst alignment to domain knowledge. So we could be sort of over-indexing on correctness at the expense of the model's ability to generalize. The other thing that's cool is that it reveals how we could elicit more aligned behaviors at generation time. So for instance, when we worked with language model researchers, they saw this fact that the model was cumulatively much more confident in artist or creator, and they suggested new ways that we might be able to do model generation. So instead of taking the most probable output, which is photographer, they could set a cumulative confidence threshold and then move up the knowledge graph until they reach that threshold and output a more general answer that the model is confident in, like artist or creator, and ultimately result in a model that generalizes more similarly to the way a user might expect. And so by measuring this alignment to domain knowledge, we're not only necessarily revealing issues in alignment, but also supporting people in solving those problems. We also found that measuring alignment to domain knowledge can teach us something about human knowledge. So during a participatory dataset audit of a medical dataset, we did the same process that we all just did with our model, but instead here we're applying it to a dataset to see if our dataset reflects the domain knowledge its creators expected. So we're looking at a medical dataset that contains clinical notes, and they're paired with medical codes that describe sort of what brought the patient to the hospital, what diseases they had, and what procedures they received. These medical codes are defined by the World Health Organization, and they're actually really important. They're what a hospital uses to bill your insurance after you've been there, and it's also what is used to compute epidemiology statistics. So it's important that we validate that how the data set is applying these medical codes is accurately reflecting the World Health Organization's coding standards. And these coding standards are conveniently in this knowledge graph format, so we can use abstraction alignment to help us do that. We worked with 4 healthcare professionals on this who all do this task of medical coding and are really familiar with it. And they were able to use abstraction alignment to understand how this data set did or did not align with their expectations. So for instance, when they looked at medical concepts that were most likely to co-occur, sort of at any level of generalization, they found that many of these code pairs made sense, like diabetes and hypertension, because patients with diabetes commonly get hypertension and vice versa. But they also noticed that many of these pairs contained an other code, like other metabolic diseases or other forms of heart disease. And our experts got really worried and red flagged this and said, our job is to code to the highest level of specificity, because the more information you have, the more likelihood the insurance claim gets paid. Right? They worried that models trained on this data set could over apply these unspecified codes and then result in persistent insurance denials. And I think this case is interesting because there's a misalignment here, but it's not actually between the data set and medical knowledge. It's between the way that we represent medical knowledge and experts' real-world experiences of it, right? There's nothing in that World Health Organization knowledge graph that says that other codes shouldn't be applied, right? All the codes are equally valid. It's that when our users were able to use abstraction alignment to surface this, they realized that the sort of coding standards weren't reflective of their own experiences, that if they used underspecified codes, their insurance claims would get denied. And so this actual issue of underspecification in the disease classification system is something that the World Health Organization updated when they went from from the disease classification system version 9 to version 10. And so I think this starts to point at the fact that, we can study alignment in this sort of domain-specific setting as a way to actually improve our own knowledge, not just our models and our data sets. And so by measuring whether a model reflects a user's domain knowledge, we get insights into how models behave and what knowledge data sets actually reflect. With this knowledge, people are empowered to improve their AI pipelines, such as generating new model generation strategies that make models more human-like in their ability to handle uncertainty. And we find that even misalignments can be valuable, right? They can help us find flaws in our own knowledge and to fix them. And so across these projects, we see how this process of reconciliation helps people improve their AI interactions. And I think this is exciting because we often think that if we want to improve people's AI interactions with a model, we need to improve the model, right? We just need to wait until Claude or OpenAI or Gemini gets the new push, and then things will be better. But here we see that people can improve their interactions just by understanding their models better. And so I think that suggests that the way we design interactions might be just as important to alignment as the way we design models themselves. So across this process, this process of reconciliation shifts how we think about what alignment is and how we can achieve it. So right now it's this developer-side process where AI experts collect data sets of human preferences and then are in charge of making their models reflect that, and then sort of deploying them across all of us as universal tools. And the assumption has largely been that alignment is a generalizable process, right? We can take human preferences, we can generalize what's important, and in doing so, we'll build models that work for everyone. But when we give people the ability to reconcile with their models' representations, we find that alignment is contextual. What is sort of ideal knowledge to me might not be to you. What's ideal reasoning in one domain might not be in another. And so who and what we are aligning to is a function of context. And by giving people the ability to understand what their model thinks and how it represents their domain, they're able to improve their collaborations with the model, they're able to improve its alignment, and they're even able to learn from its representations. And as we involve people in this process, we also saw how we might be making assumptions about what people expect from a model that might be incorrect. So I want to go back to something that happened when we were doing shared interest, and we were working with a dermatologist. And this was their explanation for their diagnosis. It was, most of this skin lesion we see here. And we expected them to want a model whose explanation looks something like this, that was very aligned with their reasoning process, using almost the exact same set of features. But what they actually were hoping for was a model's reasoning that might look something like this, where it relied on enough of their features that they felt like it was also using something medically valid, but perhaps was learning something additional beyond what they could do, right? That maybe it was seeing indicators of melanoma in these surrounding skin regions that they weren't seeing. And as a result, they hoped that their model would be able to help them catch melanoma earlier and provide better clinical care to their patients. And what I think this makes clear is that people don't want to collaborate with a model that's identical to them. They want to collaborate with a model that can complement them. But we're kind of seeing the opposite happen, right? So models are getting more and more aligned across the sort of three big families of models. We see that misalignment is going down over time, so alignment is going up. But at the same time, we're not really being amplified, right? Studies in science have shown that using AI tools reduces sort of the breadth of hypotheses we produce. In design, we see that AI is reducing the amount of creative or divergent thinking that we have. And in writing, we're producing less original content and actually thinking about that writing less. And so alignment doesn't seem sufficient if our goal is human amplification. And so if we want to design AI systems that amplify people, then I think we need to start thinking about beneficial misalignment, right? Obviously, alignment is still important when we're thinking about goals and values. We want our models to be functional. We want them to be safe. But for the sort of domain-specific forms of alignment that we've been talking about today that happen in context with a person, what if instead of thinking about aligned knowledge and aligned reasoning, we could think about designing for complementary knowledge or complementary reasoning, and then using these tools of reconciliation as a way to ensure people can benefit from that difference? And so I think the most direct way that we can help people take advantage of misalignment is to allow them to identify those misalignments directly at interaction time. Right, with semantic regexes and shared interest and abstraction alignment, people used those, but they were auditing tools sort of before they interacted with it. It helped them understand their model, inform their interactions, and then they'd go off and use the model. But what if we can enable users to understand and control these representations during interaction, right? What if when chatting with your LLM chatbot, you could see the knowledge and reasoning that it's reflecting, right? Sort of shifting these tools of reconciliation from auditing tools to end user processes. And could we allow people to change those representations to better reflect what they expect, right? Could we actually edit some of these concepts and instead of having an AI expert critique my abstract, perhaps I could have an HCI expert critique my abstract. Ultimately, sort of giving people the ability to identify and control the misalignments that their models represent. And so with this ability to handle misalignments during interaction, I think the question becomes, could we actually design for optimally misaligned models that complement their user, right? The same way that we build diverse teams of humans because we bring complementary expertise to the table, could we try to design optimal AI collaborators that are equally complementary, right? Could we use methods similar to those that we've seen today, to select or potentially optimize for AI collaborators that are not sort of so different from us that we're misaligned, but also not so similar to us that we're replicated, right? Just different enough that they can be complementary. And in doing so, could we design models that don't just sort of put on a persona, but actually represent the world in a different way, right? Could we provide a radiologist with a model that reasons just like a pathologist? Or could we give a chemist a model that thinks just like a biologist? And finally, as models sort of trend towards superhuman intelligence, could we use these tools of reconciliation to help us learn from them? So for instance, if our model actually had learned new ways to diagnose melanoma, could we identify what those ways are and then teach them to people, right? And ultimately better our own medical understanding of cancer warning signs. And then with tools to learn from models, the question becomes, could we use models to learn from ourselves? So a recent trend has been to personalize models to a particular user. And but as people, right, we have tacit knowledge. We have knowledge that's hard to express. The way that if you've ever worked with a really experienced designer, they might just be able to tell you that your design is not going to work, but not necessarily be able to tell you why. Or the way that a really experienced researcher has research taste and is able to kind of know which hypothesis you should choose without necessarily knowing how to teach you that. And so this unspoken expertise is something that typically takes sort of years of being an expert at something before you really attain. But could we use reconciliation of these models on ourselves to actually sort of reflect back our own knowledge to us and put words to that otherwise sort of hidden knowledge that we have? And in doing so, can we sort of build towards a future where people are amplified by their AI collaborators rather than replaced by their AI replicas? And so with that, thank you so much. This is typically where I stop for questions, but I have acknowledgments. Okay. So first and foremost, thank you to my thesis committee. To my advisor, Arvind, I always say that my PhD is, I think, the best job that I will ever have. And so much of that is thanks to having Arvind as my advisor. He told me one time that when someone comes to him with a research idea, he feels like his job is to help that person make that idea as great as it can be. And I think that just says so much about who Arvind is as a scientist and as an advisor and as a person. He's able to critique without being critical. And I know that my ideas have undoubtedly been bettered by bringing them to him for 6 years. When I think about what I'm going to miss most about this PhD, I think it's going to be our weekly research meeting that has just been somehow filled with like both deep scientific arguments and like constant laughter. So I can't really thank you enough. Martin is on my thesis committee. Martin was the first person whose research I saw and thought, that's what I want to be doing. So I was a fan for Martin's work for years before we actually met. And when we did meet, I was a first-year PhD student, and he was our HCI seminar speaker. And I remember I was so nervous. I was preparing for days for this like 30-minute conversation. And I went into our meeting, and I introduced myself, and I said, hi, I'm Angie. And Martin goes, I know, I'm a big fan of your work. But I think that's just who Martin is. Like, he's so kind, and he's so welcoming, and he's so excited about science, regardless of who is the person doing it. Biking over to Harvard and picking his brain has both made this research better and has also just been, such a joy. So thank you so much. And last but not least, Mitchell. Mitchell joined the department this year, and despite the absolute craziness that I know comes with being a first-year faculty member, he's never hesitated to make time for me, to help me with my job search, my research statement. He's heard this talk before, so bless him for listening to it again. I've been so fortunate to have him through this later part of my PhD, and MIT is really fortunate to have him too. The research that I talked about today is the result of so many collaborations. Thank you to my students and collaborators. You've made this work not feel like work at all. It's been such a joy. And in particular to Srini, who's been my academic advisor for over a decade now, and been such a support to my career. Every time we meet, you've somehow tied together these like incredible wisdom nuggets about research and teaching with like some like absolutely ridiculous, hilarious story about like getting caught in a riptide in Hawaii. I was also really fortunate to spend time during my PhD with some wonderful folks at IBM and at Apple. A huge thank you to Hendrik, who was an integral part of the research I presented today, and also my career as a whole. He was the first person who encouraged me to organize a workshop with him. He's always inviting me on coffees or on trips to meet other researchers in our field, and he throws a really, really good holiday party. So if you ever get invited, you should definitely go. And to my Apple mentor, Fred, I admire Fred so much as a researcher and a designer. I think you can actually look at my papers and determine before and after I worked with Fred, because he taught me so much about design and polish and communication. And so I'm just really grateful to everyone on this slide. The Viz group is so special to me. They are the most supportive group of people that I've ever had the pleasure of working with. And I know everyone says that, but I'm actually going to give you 2 stories that I think are going to prove it. First is that our Slack channel is just filled with messages like this. Whether you won like the biggest award on the planet, or you like presented a poster at like the most random workshop that's ever existed, you're gonna get, someone's gonna shout you out in the Slack channel, and you're gonna get about 1,000 whale emojis and like a whole thread of congratulatory messages. And 2, the top hand corner is just one example, but I think we've done like almost every escape room in the Cambridge area. And despite some like very stressful buzzer beating escapes, no one has ever snapped at each other or argued, not even once. And I think that really says something about just how kind and how supportive this group of people is. I'm really fortunate to have them in my life for this PhD and hopefully for many years to come. Thank you to my friends. I have friends from high school who are on Zoom today who had no idea what a PhD was when I decided to do one, but just wholeheartedly supported me the whole way through. People from undergrad who have just been there for all the celebratory moments. And then so many friends throughout this PhD that have been there to talk about research and then also importantly talk not about research. I can't thank you all enough. In particular, I have a really special group of friends. Our group chat name is Grad Girlies. Many of them traveled in to be here and rearranged their travel plans to be here today. We got to start our PhDs together, which has been really special because it means that we've been there for every milestone, right? We were there for each other's first publication, for every failed and then eventually successful experiment, graduations and engagements and weddings and defenses. Most of these things we celebrated over a wine night and like so much laughter. But I do think I knew we were like getting towards the ends of our PhD when our wine nights started becoming coffee afternoons. That's kind of when this defense needed to be scheduled. I have a really dear friend, Rachel, who traveled from Utah to be here. I'm a computer scientist and she's a nuclear engineer. And so we have a running joke that neither of us understands what the other person does. But after today, there's no more excuses for you. But despite not knowing what I do, she is my all-time favorite person to FaceTime because she will not hold back on roasting reviewer 2 for you after they reject your paper, or hyping you up for a big talk, or just making you laugh when you need to stop thinking about research. So yeah, thank you. I have an incredibly supportive family. I'm a first-generation student and also the first person in my extended family to get a PhD. So as much as this is for me, in some ways, I think it's also for all of us. So many of them are in Zoom today. I think my grandma's even on Zoom. Hi, Grandma. And my aunt and uncle flew in from Canada to be here, which has just been such a staple of my life. They were here to help me move in. They've been here for every graduation, or just to like catch up over like pasta and a modern pastry lobster tail. I also have the most incredible in-laws. And much of this PhD has been fueled by their incredible Italian cooking and the vitamin D that I get from visiting them in Florida. A huge thank you to my parents. I grew up on a farm, and people are often surprised by that, but I actually think farming is the original science. And while growing up, the hypotheses we debated around the kitchen table were less about AI alignment and more about crop yields and cattle health, my love of science is definitely thanks to them. My mom is the only person besides me, I think, who's actually read all of my papers. And despite having no background in computer science, she will call me and ask questions about them. And it just feels like if someone loves you enough to read your iClear supplement, you're really, really lucky. So thank you. And finally, to my husband, Brandon, you've been so many things to me throughout this journey. When we started, we were partners. Then we actually both applied to PhDs at the same time and got in, although I was slightly ambitious on my timeline, but that's fine. You were the co-author for the first paper that we published during this PhD. You also became my husband throughout this PhD. And hopefully, if things go well today, we will both have PhDs and we can recreate this photo. But more importantly, you've just like filled our life with so much fun and adventure that I'm really fortunate to say that this PhD is only one of the many joys that I get to share with you. And so with that, I will actually stop now. Thank you all so much, and I'm happy to take any questions. Hey, Sherwin.
You know, I'm in business. You find AI dangerous, or case involved with when a trial took place and the research was done by AI. And because AI could not send an answer, it created its own answer and made it up. You find that as we get more and more knowledgeable with AI, it'll start doing the thinking for us.
Yeah, that's definitely a huge concern, right? It's this idea of, I think when AI models are designed to replicate us, right, we can offload more and more of our thinking. And as a result, we can get more complacent. And we see that all the time, actually. Like, even before we got large language models, we had, when we showed people model decisions and explanations, it was just like too tedious of a task to be double checking your model all the time. And so people didn't do it. And people actually performed worse when they interacted with the model. And so I think that's very similar to the situation you're describing and the situation we see, right? Where people are using these AI models in tasks like law and science, like in creative writing. But we're actually not getting that complementarity we're hoping for, right? We're not being amplified by our models and getting to be, faster at our jobs or be able to be better thinkers. We're actually kind of just like offloading that critical thinking, and then we're ultimately as a team getting worse. And so, yeah, I definitely think it's a big concern, and I think it's a problem that we solve via like design, right? Like, how can we design models to support us in being able to sort of like use our energy most effectively, right? Like, how can we have AI models that help us think critically when needed, that do the tasks, the simple tasks that maybe we don't have to think really critically about, as opposed to sort of just trying to do exactly what people do and, so that I can offload everything to my model. So yeah, I think that's you hit the nail right on the head. I think you understood the talk.
Regarding semantic regexes, is it a purely analytical tool for now, or do you thought about applying this to generation architects?
Yeah, right now it's a purely analytical tool. So it's like a way to, once you find a feature in your model, it's a way to describe it. But I do think there'd be cool applications in terms of, could you take that, both ways. Could you take that and use it as a way to sort of help you do tasks like circuit identification or like find feature redundancy, right? So in those sort of tasks, but I also think it's related very much to like Malaya, right? And how you could sort of define the syntax for generation as well, or define the syntax for like model steering. And so, I think there's lots of places where we can think about sort of how we define the syntax of structured languages to better sort of reflect both what models are doing computationally, but also reflect what we expect them to be doing. So yeah, let's talk more. Yeah.
I really like your distinction between complementarity and replication. And it seemed like in a couple of the examples, complementarity was just replication of someone else, like in components. And I wonder if you see a separate axis where there is complementarity that's not exact replication.
Yeah, that's a really good point. So yeah, sometimes complementarity looks like having an AI represent a different perspective, like someone else's perspective for you. But I do think there are cases where it doesn't necessarily mean replication of someone else, right? I think if we think about models learning novel representations, then I think that that's a case where you're not sort of replicating someone else. I also think there might be cases where like models could support collaboration between people and sort of do like facilitation. But yeah, I think it's interesting to think about how we design that, and also if it tells us anything, like either whether we can take inspiration from how human teams exist, or if by having human AI teams, we can learn something about how to design better human teams too. So yeah, great question. Yeah, Amber?
Yeah, the complementary stuff was really interesting. I'm really excited to see where you go with that and your future research on that. I was curious about how you think that overlaps with a hot button issue of like sycophants that people have been talking about, where I feel like these models have been trained to be sort of over eager to read. And it feels like should be enforcing morally that these complementary sort of representation might require not only assuming like the knowledge that the model has, but also the behaviors and the animations that it chooses to so I want to like pick your great brain up what you sort of see as these like kind of two main knobs that are kind of considering.
Yeah, totally. I think you hit the nail on the head. Yeah, I mean, I think a lot of sycophancy is sort of an artifact of how we currently think about alignment, right? It's when we're sort of creating these data sets of human preference, I think we're sort of simplifying what human preference is. And oftentimes in a sort of a setting that's not always realistic of like how things are in the real world, right? Like I might like that I find anyway, the first time I ask my model something and it's like, wow, such a great draft. I'm like, oh, thanks, model. I thought so too. But like when we're like 40 messages deep and like, I'm like, this is not a great draft. Like, stop telling me, like we both know this is not good. And so I think sycophancy is a symptom kind of the way we think about alignment currently, that it's generalizable from across a whole bunch of people, that it's sort of generalizable from like a single response to like a full-fledged collaboration. And yeah, I think that like, there's this idea that comes from like beneficial friction, right? That like having, some of my favorite scientific conversations have been like borderline arguments, right? Where someone pushes back on you. And I think there's a place for that, and there's also not a place for that. Like if we pivoted all the way and every time I talked to my model, it was like, your draft sucks. That also wouldn't be good. Yeah, so I think the communication piece is also really interesting. Yeah. Yeah, Han.
Thinking about misalignment. Do you think that the misaligned space of possibilities is more structured than the random space?
That's a good question. You mean in a particular model, or you mean if we were thinking about the entire design space of models?
In a particular model.
Yeah.
Utilizing it for certain findings.
Yeah, I think definitely. I mean, I think it'd be interesting to better understand, like, we have models that can like put on personas, right? And I can say like, oh, act like a biologist. But I don't think we fully understand like what part of the manifold like represents biologist, and is it like sufficient, right? And like where do we draw, like whose perspectives can it not represent is like unclear, right? There's probably holes in there of yeah, exactly. I don't think we know the answer to that, but I think it would be helpful to know, right? Like to know, can my model actually reflect this perspective if I find the right way to ask it or prompt it or shift it internally? Yeah.
Anyway, I love the presentation.
Thank you.
One question about the complementary, I'm curious about how do you measure that in terms like an eval? And the second thing is, when you're doing the problem framing and the method, all these, have you come across, to what extent have you come across the outer alignment versus inner alignment issues?
Yeah. In terms of metrics for complementarity, I mean, I think we can sort of take inspiration from some of the metrics we have here, right? Like we have metrics to think about whether reasoning is aligned. We have metrics to think about whether knowledge is aligned. And so I think there's questions about like, I think it's like, there's a question of like how alignment conforms with complementarity, right? Like where does it maximize and where is it minimal? And so I think there's space for like a lot of human studies in this. And I think that hasn't been part of sort of the machine learning paradigm in terms of we want benchmarks that are really easy to run over and over and over again, and human studies aren't necessarily that. There might be something in like the way we're currently thinking about like agent simulation that might like point us towards a place, but I think there's also lots of space for just understanding how people actually interact with these systems over long horizons, when they're interacting with many models, when there's many models interacting with people. And so I think there's a whole space for how do we develop evaluation metrics of that. Your second question on like inner versus outer alignment. Yes, so like a lot of the work that I've talked about here hasn't been focused as much on like how we traditionally think about alignment in terms of like a safety thing, right? Where our model might be saying that it's safe, but actually isn't reflective of that internally. A lot of what we've done here has either focused like just on the internals or just on the outputs. But it would be really interesting, I think, to take some of these ideas like in abstraction alignment, we're measuring it based on the model's like output purported confidence, but you could equally run the same method, but actually if you could find like concept features in the model and then do it with activations as opposed to output probabilities, you could kind of measure like the abstraction alignment of the model's output versus the abstraction alignment of its internals, which I think would be, really interesting to see how much that's true or not. I think it would be different than the case we traditionally see where we are thinking about misalignment as like malicious intent, because I think that some of that comes from like the data it's seen, in the sense that like, you know, we have this like big like AI boogeyman kind of like sci-fi situation. And I think sometimes that's what comes across when it's like the model is saying the right thing, but it's not reflecting it internally. Whereas I feel like when we're thinking about like reasoning or knowledge, there's probably less of a sort of like influence to lie or like just seem aligned, right? Like when it's like whether you know an oak is a tree, there's probably less sort of pressure to lie about that. But we haven't run that experiment, but it would be really interesting. Yeah.
I really like your second work where you basically compare the output of the model to a human specified taxonomy.
Mm-hmm.
Do you think it makes sense to do kind of the opposite, where you use that misalignment from the model to build the model's own taxonomy?
Yeah. Yeah, definitely. So we actually did explore that a little bit, where we would essentially start with like a predefined set of nodes, and then we would like merge them based on like what would minimize the entropy, and then we'd like build up a knowledge graph. It just became really complex when you're dealing with like a really large, and like it was pretty much intractable if you wanted to build like a graph of the size of like WordNet.
What about within a context? So then the status is small.
Yeah, it's possible. So like we did a few experiments on that, and then it became really time consuming and we didn't push it further. But I do think that'd be really cool. Or even I think it'd be interesting to see if you could like extract. So like that would be extracting it based on like the model's outputs. But I was also thinking it'd be interesting if you could extract it from like the model's input features or like internal features space as well, right? Like, is there some sort of like hierarchical knowledge graph that exists in there? There's been some work showing that like hierarchical like sentence parse trees, like models encode sentence parse trees, which is kind of like a knowledge graph if you think about it like in context, right? So that you can map, this noun matches to this adjective, etc. And so, yeah, I think it would be, very, very cool. Srini.
Very nice talk, Angie. I'll figure out how to ask at least one question. It's a layperson question. What a computer sees in a scan isn't what the doctor sees on their screen, right?
Yes.
And what a person hears isn't what a computer hears. So how does that fit into all of this?
Yeah, I mean, I think that's what makes this setting different from like human to human collaboration, right? Is like, I think like in the paradigm we're in now, we're kind of like, we're talking to a model the same way we talk to a human, but then under the hood, you're exactly right. Like, it's not the same as when I talk to a human, right? Like I don't know if we share the same domain knowledge. I don't know if when my model looks at an image, it's doing the same sort of feature extraction or like whatever my brain is doing when I look at it versus whatever a doctor's brain is doing when they look at it. And so I think that's like exactly what makes this problem hard. We've solved a lot of like reconciliation of mental models in human to human interactions, like over time. But I think a lot of that comes from we have the sort of baseline understanding of how other people are thinking. There's like some basic understanding of how you perceive the world. And so I think that's like exactly why this is not as straightforward as it is in human interaction. Raquel.
In your set of the data and your interaction that you went through, you noticed any temporal changes to people's desire to learn? Thinking back, there's a dependency question where maybe at first you want people to, or you want the model to encourage and eventually get tired of it.
Yeah, that's a good question. We didn't typically study things. We have never like studied in like multi-turn interaction settings, but that would be interesting. I think that happened a little bit in shared interest but I think this was maybe more people getting used to the idea of like what alignment is, right? Like for a physician who's coming to the idea of alignment for the first time, at first, lots of them are like, well, let me see exactly when the model agrees with me. And then they slowly, like as they saw more and more examples, got like more and more intrigued by the ones that maybe they had some misalignment, and they were like, "Ooh, that could be interesting too." So I think that's like really the only evidence I have to kind of support what you're saying. But I do think it would be interesting to see how even expectations change as you work with a model for longer and longer. And I think that sort of points to the fact that then we have to negotiate this in interaction, because if what I want in my like very first chat with ChatGPT is different than what I want on my like 80th like agent spin up, then it means that like we can't just figure this out and then like throw the model out to everybody.
So I might suggest that we perhaps bring the public Q&A to a close, and Angie still has to weather the private session. So please join me in congratulating Angie on a brilliant